Postulates and diagrams is what we're talking about today. Now, we really haven't even hit our first few postulates yet. We're starting on 5, 6, 7, 8, 9, etc. 1, 2, 3, and 4 we get later. But let me just very quickly go over what these are. A postulate, it's a big fancy word, is simply a rule of geometry. These are one of our rules, our very basic rules that we don't even need to prove. They're just so obvious we accept them to be true. A lot of times they are making very easy things sound complicated. But again, these are things that are stating really obvious truths. We're just establishing them as, okay, yes, we accept this as being true. We all agree that this is a true statement. That's what a postulate is. A theorem is also a rule of geometry, but that is a rule that we need to prove is true using a deductive reasoning format. So postulates and theorems are both rules. Postulates, and some books refer to them as axioms, are accepted without proof. Theorems are things that need to be proven using deductive reasoning. Now, a lot of times we don't use the number of the postulate so much as we do what it says, because the numbering of postulates is not uniform. You're probably wondering, why does anybody keep so many geometry books on their shelf? Well, this might be one of the reasons why. Let me just grab something here. I'll grab this one. I'm just grabbing a random geometry book. While postulates, the rules are generally accepted throughout all the geometry books and all different ways that geometry is taught, the order in which they're presented is not standard. So our postulate 5 says, through any 2 points there exists exactly one line. In this book, I got to find where they list their postulates. They probably do somewhere. No, they don't. Well, that's not going to help me very much then. Let me pick a different book. This one isn't going to work with me very much. Let's try, bad luck on that. So it happens when you pick randomly. Sometimes it doesn't work. Extra practice, chapter test, postulates. Okay. In this book, they don't even have a postulate 5. They call, through any 2 points there exists exactly one line, they call it postulate 2-1. So chapter 2, first postulate. All right, exact same wording, the exact same rule is here, but it's numbered differently. So one thing you should understand very quickly about postulates is that the author of the book, whoever's writing the book, can determine their own numbering system and their own ordering system for postulates and theorems. So we don't necessarily want to get hung up on, oh, that's postulate 5. Because if you were to switch schools, or if you were to go to a college class and be asked about this, and they say, well, which postulate tells you this? And you said postulate 5, they might have no idea what you're talking about. Who cares what number it is? What does it say? What does it mean? So let's take a look at these postulates. These are stating very obvious things, but very specific things. Through any 2 points there exists exactly one line. Any 2 points. So if you pick any 2 points at random, you can always draw a line between them, can't you? And lines are infinite, so that line goes on forever. Postulate 6 says a line contains at least 2 points. Wasn't that what we just said? Not at all. Not at all. They are, in a way, converses, but not even that. They're even more. They're not actual converses. One says much more than the other. In this one, we start with 2 points, and we conclude that there's a line. So through any 2 points, that's our if, that's our hypothesis, we conclude there's a line. This one we start with a line, and we say it has at least 2 points on it. How many points? Well, at least 2. What does at least 2 mean? 2 or an infinite number, or 17, or 962,504. At least 2. Quite possibly and actually more. So realize these are not saying exactly the same things. These are covering different situations. This is when I am given 2 points, I can make a conclusion as a line. This says if I have a line, I can make at least 2 points on that line. Postulate 7, if 2 lines intersect, their intersection is exactly 1 point. We kind of looked at this the other day. What happens when 2 lines cross each other? The intersection is how many points? 1. Can 2 lines intersect at more than 1 point? Not in plane geometry. See, we're studying what's called plane geometry, or Euclidean geometry. Geometry on a flat surface, in a plane. You're saying, yeah, how else would you study geometry? Well, we could do spherical geometry. Spherical geometry is geometry on the sphere. Why might we be interested in that at some point? Well, gosh, we live on a sphere, right? The planet is a sphere. So that could be very useful for us. We don't have to worry about that right now, but it can be real. It's something that if you go on and study math at higher levels, you'll get into spherical geometry and stuff like that. For now, we're just going to worry about plane geometry, and these are rules that exist for plane geometry. P-L-A-N-E, not P-L-A-I-N. Okay? A plane as in point line plane. Yeah, don't worry, I got answering that gets that. Postulate 8. Through any 3 non-collinear points, there is exactly 1 plane. More commonly stated, 3 points make a plane. 3 non-collinear points make a plane. Why is it important that they're non-collinear? Let's think about that for a second. What if I had, here's a line, so I can make collinear points nicely. If I have 3 non-collinear points, there's only 1 plane I could put through that, right? That's what our postulate says. I could only make 1 plane that encompasses them. But if I have 3 collinear points, like that, how many planes go through those 3 points? Well, we've got the 1, the plane of the smartboard, right? But I could create another one that's coming out this way, couldn't I? And that would also have all 3 of those points. Or one at an angle coming in like this that intersects that line. And again, that would have all 3 of those points. So it's important that the points be non-collinear in order to get a plane. If they're collinear, we get a potential infinite number of planes going through it. If they're non-collinear, there's only 1. And again, notice we start with 3 non-collinear points. Our conclusion is a plane. This is the reverse of that. A plane contains at least 3 non-collinear points. There we start with someone tells you, hey, you got a plane out there. The plane, we're going to call our floor of the plane. How many points does it have? It's got to have at least 3 that aren't all in the same line. How many does it really have? An infinite number of points, right? I mean, heck, even if you consider every speck in the carpet a different point on the line, that's an awful lot of points, isn't it? And there's way more than what we can see, so it's an infinite number. Postulate 10, if 2 points lie in a plane, the line containing them also lies in the plane. Well, I guess where else would it be, right? And again, let's think about that for a second. These are kind of thought pictures here. I have 2 points in a plane. So somewhere if someone's drawn a plane, I could actually do it, I suppose. We'll move this away. Get rid of that. there's a plane. The smartboard here is a plane representing it, and points A and B are part of that plane. Well, guess what? The line that contains points A and B, that line right there, is also in the same plane. There's no way it could be in a different plane, could it? If the points are in the plane, the line that contains those points must also be in the plane. That's probably making your head hurt right now because it's so obvious, yet it seems weird to say it. But it makes my head hurt a little bit. But that's okay. That's one of our basic rules. Again, these are things that are supposed to be fairly obvious. Finally, if two planes intersect, their intersection is a line. And we can see that all over the place. If you consider the wall over here a plane, and this wall in front here, also a plane. When they intersect right here in the seam, right? And that would be a line, wouldn't it? It's not a point. It's a line. Or the plane of the ceiling and the plane of the wall. Again, you can see along that edge where they intersect, that's a line. Now, this is why we're going to use a lot of this stuff. And you're probably going to see this on your next benchmark as well. I'm telling you right now. What we're going to do, and even though I've kind of said, we want to be careful about using postulate numbers, we do. So when we see a problem like this, what we're going to do is we can use the postulate number, but we also want to state what the postulate says. So what I'm doing is giving you a diagram, kind of a conditional statement using pictures. And you have to tell me which of the postulates is being illustrated by this picture. So here I say if, and I've got this, then I've got this, and they added the red dot in the middle. Well, what am I starting with here? If I have what? What are these two things? If I have two lines, then what are we adding? A point of intersection. Which postulate says if two lines intersect, then their intersection is exactly 1 point? Which one is it? Obviously number 7 that we're illustrating there, isn't it? So we got to match up the words, the postulate number, the identifier of it for now, and the picture. And I'll give you the picture. All right, so this would be an example of postulate 7. If two lines intersect, then the intersection is a point. And yeah, it took me a few seconds to write that. Oh no. Take a few seconds and write things out. The physical act of writing it out helps you remember. All right. Interpreting a diagram and making assumptions. This is important because a lot of times we tend to want to make assumptions based on a picture. Sometimes we can do that, sometimes we cannot. We have to be very careful what we assume and what we don't based on a picture. Here I have a picture of a plane with some points in it. In fact, well, no, I can't expand that. Okay, I thought maybe I could separate that. No, okay. And we've got these different points here, et cetera, et cetera. Well, some things we can assume. I can't assume all the points drawn lie in the plane because it appears they do. I can assume that AHB and BHD are a linear pair. We haven't really talked about linear pairs yet, but let's look at that. AHB and BHD are a linear pair. They're a pair of angles, they make up a line. You could consider, maybe put it this way, if you put those angles together, they make a straight line. Okay, because it looks like a straight line, it is a straight line. Vertical angles we also haven't talked about yet, but we'll get to that later. We won't worry about that now. This is important. A, H, J, and D are collinear. I can assume that all of these 4 points are collinear because they're drawn on the same line. And AD and BF intersect at point H, yeah, I can make that assumption. What are some things I have to be careful not to assume? That GF and E are collinear. See, people love to look at this and say, hey, these 3 points are on a line too, aren't they? Looks like they all line up. Must be a line. You don't even take a ruler and go, see? We can't do that. We can't make that assumption. Now, I could assume that G and F form a line. Because any 2 points make a line. That's postulate 5. And I can assume that F and E make a line, but that doesn't mean G, F, and E both make lines. You're saying, well, but if G and F make a line and F and E make a line, doesn't that mean they're all in the same line? No. What if G was here, F is here, and E is down here? Now, granted, it's an exaggeration, but what if that's the case? Just because G and F are on a line and F and E are a line doesn't mean that G, F, and E are all 3 on the same line. Okay? They're 2 different lines. F is part of many lines by itself. Would G and E be on a line? Why? You said yes. Why? Yeah? Because any 2 points make a line. Yeah. It wasn't drawn in, but sure enough, it must be there. Do not assume that these 2 lines, BF and CE, are going to intersect at some point. If the point of intersection is not shown, it cannot be necessarily assumed. They might be parallel. We also can assume the opposite, however. We can't assume that they are parallel. We don't know if they intersect or they don't intersect, because we don't have the entire picture, do we? We only have a small portion of those lines. We would not want to assume that angle BHA and the angle CJA, let's note where those are. BHA, and CJA are congruent angles. I may not assume that. I would need a lot more information to make that conclusion. They kind of look the same, doesn't mean they are. Kind of look is not proof. Measure AHB is 90. I can't assume that that's the right angle. I have no idea what the measure of that angle is. It looks to be obtuse, but again, depending on the perspective we're looking at it, it may or may not be. But I certainly am not going to make an assumption that something's at right angle unless I'm told it's a right angle. So when we look at pictures, we have to be careful that we don't make assumptions that are unwarranted. Only take what is given to you. Don't read into it. Don't add to it. All right, here's another picture. If blank, then blank, we add the line. What are we starting with here? If I have 2 what? Planes, then they intersect in a line. Do all planes intersect? No. Ceiling, floor. Think about that. They shouldn't. If they're intersecting, we get a problem. Okay? Which theorem was that? 2 planes intersect, their intersection is a line. Which postulate? What do you have? Yeah, it's not hard to figure out when you're looking at the slide, is it? That's why these note cards may be helpful for you, if you've done these note cards. You have these postulates written out, maybe even with a picture. You can put them in front of you. You don't have to flip back and forth like I'm doing right now, except you're using pages. Whoops. Draw a picture that contains this. A plane contains at least 3 non-collinear points. So what are we going to start with? If we have what? A plane. Let's draw a plane with nothing on it. Then, how many points? 3 non-collinear. Getting the idea how this stuff works with the pictures? Pictures are our friends. Get used to them. We use them a lot. Okay. Let's take a look at each of these statements. Can we assume these statements are true? A, B, and F are collinear. Can I assume that based on my picture? Yes, because they're all drawn onto the same line. E, B, and D are collinear. Can we assume that? No, why not? Well, fact is we're not sure, are we? Because nothing's drawn in to indicate that all three are on the same line. How about we just put E and B are collinear? Can we assume that? E and B? Sure, because any 2 points are collinear, right? AB is perpendicular to plane S. Notice plane S here is the red plane. AB is perpendicular to it. Is there anything there to indicate the right angle?
No. Yes.
Yes, there is. There's a little box there, isn't it? So we could assume that. CD is perpendicular to plane T. Blue plane, CD. Can we assume that? Is there any box to indicate that right angle? No, so we can't assume that. AF intersects BC at point B. AF intersects BC at point B. Can we assume that? Yes, because it's drawn in. So don't leap to conclusions based on what is drawn in and what is not. Kind of a hard picture to see. What we're doing is, this is a new construction, new drywall. These are like the electrical boxes that you see here. It's like a kitchen with a half wall coming out here. All right. I do need to sign your passport before you go, okay? So we can talk about seeing things illustrated. So if I talk about, and it's a little bit tricky to see, not the best picture. But there's a small wall, and then here is another wall that goes back, way back in there, okay? So this wall is intersecting that wall. What do we have being demonstrated here? This wall would represent a point line or plane, okay? And this wall that's intersecting it would represent another plane, and then the two planes intersect. Their intersection is a line, okay? Thank you. Yeah, they've been kind of hollering at people, letting people go without passports. So, how about if I connected these two electrical boxes here and said there's a line connecting them? So I grabbed those two. I started with the electrical boxes, and then I went through there and said there must be a line that connects them. What am I demonstrating? Through any 2 points, there's exactly one line, right? Starting with 2 points, ending with one line, which is postulate. You got a list in front of your book and right in front of you. Through any 2 points, there is one line. Which one? No. Helps if your book's open. Through any 2 points, there exists exactly one line. 5. Could I draw another line through the same 2 points that's different? No, because the postulate says how many lines? 2 points. How many lines?
1.
Exactly 1. Not almost 1, not at least 1, not at most 1, exactly 1. No more, no less. This is a way of how we can apply that. Which postulate is kind of illustrated here, do you think? I have a dart coming into a dartboard. What do you think that's kind of trying to illustrate? Is that points, planes? What would the dartboard itself represent? A plane, and the dart maybe represents a line. And when a plane and a line intersect, they intersect at a point, don't they? That is postulate. You look back at our list. I don't have one for plane and line, up here yet, do I? No. Okay. That's kind of what we'd be talking about. Another choice we might have from the ones we have here is these two intersect here, these 2 points exist, so we might be say there's a line there. All sorts of different ideas. Here I have two streets intersecting. Streets should be representing what? Lines. And when two lines intersect, they intersect at a point. That's what we're kind of drawing here. Now, you're saying that's an awfully big point. Well, they're awfully big lines. Okay? So that's kind of what we're doing. How about here? It's like a Google map of some sort. I've got 2 points. When I connect them, I get a line. Okay, someone keeps trying to call me. That's really about it. This is what we're doing today. So I'll let you have a little work time here. Yay.